This is the quiz review video for Monday. Couple definitions and equations you need to know. First, both a definition and an equation. Current is charge per second, which gives you the units of coulombs per second or amps. And there are some questions that test conceptually. Do you understand that current is an amount of charge over an amount of time? So you've got to know that. Also, there's Ohm's law, which is V equals IR. And you can rearrange that to find voltage, current, resistance. But some important things to note. Whenever voltage goes up, current goes up with it. They perform the same. They have a direct relationship. However, whenever resistance goes up, current goes down. They have a inverse relationship. Also, the two power equations that we looked at this weekend, P equals IV and P equals I squared R. For both of these, you need to know current, so if a problem doesn't give you current, you've got to come back to Ohm's law and use it to find the current. Remember, power is the amount of energy kind of dissipated or used by a resistor as it heats up. You'll be asked to make some VIR charts and figure out equivalent resistance. So remember that in series, when you're finding equivalent resistance, you just add the resistors, and so on. In parallel, the inverse of the equivalent resistance, you add the inverses. So you add the inverses and then take the inverse. In a series circuit, adding a resistor will always increase resistance. However, in a parallel circuit, adding a resistor always decreases resistance because you add a new path for the electricity to go through. So you make it less resistance because every time I'm adding one, there's a new path back to the battery. And so you decrease resistance whenever you add a resistor in parallel. One idea that we've used, but I never told you the name of because it's not that important to know the name, or I didn't think so. However, the AP exam, when I was looking through a couple years ago, there was a question that says, this rule deals with, and there were several options. So real quick, there's a rule called Kerkoff's Junction Rule, which we've actually used a lot. I'm just only now telling you the name because, again, the name wasn't necessarily important to using it. Kerkoff's Junction Rule says that whatever current enters a junction must also leave at the end of that junction. So let's say we have 2 amps of current leave this battery. And then here, when the current gets to the resistors in parallel over here, that current will split, and let's say half an amp, I'm just making things up, half an amp goes this way. Well, that means that the other 1.5 amps has to go the other way. Amps are the amount of current per second, and so amps tell you how many electrons are entering every second, and you're not going to lose any electrons. So if 2 amps of electrons per second leave the battery, then 2 amps are going to move everywhere in the circuit. So Kerkoff's junction rule says that the current will split whenever we come to this junction right here, but that it will come back together, so the 0.5 amps will meet back up with the 1.5 amps. And at the end of that junction, 2 amps will leave and 2 amps will return to the battery. So Kerkoff's junction rule is basically just the idea that you can't gain or lose electrons as you go along. How many ever enter at one place are going to have to come out at the other place. Now, some neat things that can come out of this. If we had, say, a resistor in series and then another in parallel, whatever current leaves the battery, let's pretend it's 2 amps again, that current must go through this resistor and come out. So those are the electrons that go in, they've got to come back out. And so this resistor here would get all the current from the battery, and then the current might split, and let's say it does the same thing as before. So the current splits and then comes back together over here. Now that also means that if I were to put another resistor down here, since the 2 amps have come back together by this point, this resistor would get 2 amps through it. So how many ever electrons leave the battery have to come back to it. And that might solve some of the problems people have been having with current. Let's also think about voltage. Voltage works like height, and no matter what path electrons choose to take, they all have to fall the same height. So if this battery is 6 volts of potential or voltage, that's kind of like falling 6 meters. No matter if an electron chooses to take this path or this one, any electron that leaves the battery must fall all 6 meters, or must go through all 6 volts of potential. And the falling only happens when you're crossing a resistor. So the electron would fall a little bit here. Let's say it fell 2 volts here. Not 12 volts, 2 volts. Say it fell 2 volts there. Well, that means no matter what path it takes, it has to fall the remaining 4 volts. So both of these resistors up here would have 4 volts of potential across them, because the electron has to fall all 6 volts. And that might be a better way of thinking about it than voltage being used up. An electron has to fall the entire height of the battery, and the height of the battery is given by its potential. I think that is actually a really great conceptual thing to understand. So if you didn't catch all that about electrons falling, maybe rewind, because I do actually think understanding that voltage is the distance an electron has to fall, and that they only fall when they're going across a resistor, I think that is kind of a key analogy to understanding how that works. Now obviously electrons are still moving through the rest of the wire, but their potential only changes when they cross a resistor. So that's the only part where they fall. I'm doing air quotes when I say fall. Alright, I hope that helps. That's all the stuff that is on tomorrow's quiz, and I will see you tomorrow.